So in a previous lecture, the Doppler effect of light has been discussed from the period point of view. So that's one way. There are other ways of deriving the Doppler effect of light. Here, we're going to use a slightly more advanced concept, which is the concept of a 4-vector. So what's a 4-vector? 4-vector is like, for example, this time and position vector. When you combine them, that's a 4-dimensional vector. That's a 4-vector by definition. And any object that transforms just like this space-time vector is called a 4-vector. So, for example, if you have energy and momentum, that's a 4-vector. Another example is if you have angular frequency here and a wave vector of a wave there, that's also a 4-vector. So what this means is that any of these 4 vectors should transform just like this T and X transformation. And because that T and X transformation is what we know as Lorentz transformation for a Lorentz boost operation, we can easily figure out how omega and k transforms from one inertial reference frame to another. So using that, we can derive the Doppler effect. So let's set it up here. In this setup, we're going to be somewhat more adventurous, so that we will actually consider the velocity of v of the radiation source particle in some random direction. We will not assume that v is necessarily along the x direction. So, but this reference frame is moving at velocity v, and we are sorry about this. This is x prime and y prime, and we are asking the question: if we observe this light coming out off of this radiation source from a rest frame here. And again, we will be kind of adventurous here. We will not assume any direction of the wave number or wave vector of the light that we observe. It could be any one of these. And so then we ask the question, what is the Doppler effect? So for example, this could be the direction of the wave vector that we choose to observe. Okay, so the Lorentz transformation that is relevant in this discussion turns out to be just one equation, and that equation is the transformation from t to t prime. So let's write it. T prime equals gamma parenthesis t minus v dot x vector. So this is the generalization of the Lorentz transformation that we've been using. We've been using Vx without the vector notation, but if V is in a random direction like this, then this can be shown to be valid, and I'll leave it as an exercise for you. And here again we are using the unit c equals 1. But now if this is actually the Lorentz transformation equation for time, then by the identification of this being as a 4-vector, what that means is that if we actually use omega prime, which is the omega that we measure in this prime coordinate system, then that should be related to gamma omega minus v. And what is the corresponding spatial vector? That's k. Oh, by the way, that's gamma in this case is 1 over 1 minus v squared. So now, so that's it. So now all we need to do is here, k equals k unit vector along the k direction. And then we know that the property of light is such that omega equals c times k, but we're using c equals 1 unit, so that means omega equals the magnitude of k. And so what that means is that this equation here, we can rewrite it as omega prime equals gamma. I'm going to factor out omega here because the magnitude of this is actually equal to omega, gamma omega 1 minus v dot k hat. The k hat unit vector along the k direction. And now you notice that omega prime is the frequency that is measured with the radiation source at rest. So that would be the frequency we might call omega 0, the true frequency of that radiation, if you like. So that's omega 0, and then the omega gamma 1 minus v dot k hat. So the Doppler effect then reads as omega equals gamma 1 minus v dot k hat omega 0. So that's the Doppler effect. That's the most general way of writing Doppler effect of light. And I leave it up to you to show that when k hat and v are parallel, that corresponds to light source approaching directly towards towards the observer. In that case, this becomes a positive number v, and that is equal. That's the same equation that we derived in the previous lecture. And also, when v and k are opposite direction, are directed in opposite directions, then this v dot k becomes negative of the magnitude of v, and that's also in agreement with the derivation that we have given in the previous lecture. In any case, this equation actually is the most general equation for the Doppler effect of light, because it also deals with cases when v and k are not collinear.